Welcome viewers to the last segment of the third lecture for the online series of lectures for the course of Dynamical Systems. We'll start this segment by introducing an example of how to compute infinitesimal generator of a dynamical system. Let us start with the example. Example 4. Let theta from R cross R2 to R2 be the dynamical system. Given in example 2. To find the infinitesimal generator of theta, find the infinitesimal generator of theta, we first compute the following. Compute del by del theta at t comma x comma y to be equal to, so we just derived the matrix representation of theta sub t, the induced diffeomorphism, which is minus sine t minus cosine t, cosine t minus sine t. Okay? And the vector xy for all xy in R2. Okay. Now using the definition of infinitesimal generator in equation number 26. Let me write the equation number 26 here for your convenience, which was the definition of the infinitesimal generator dynamical system. Del by del t theta t comma x evaluated at t equal to 0. This was the definition. For all x in U. One finds in this case f, using this formula, f of this vector, right, xy is equal to, from this, del theta by del t at t comma xy evaluated at t equal to 0. Okay, and this is going to be equal to, now, so I just substitute 0 in this matrix, right, to end up with 0 minus 1, 1, 0, this matrix. If I plug in 0 there in this matrix, I get 0 minus 1, 1, 0, right? And multiplied with this column vector xy to end up with minus yx. And this is true for all xy in R2. It then follows that the infinitesimal generator of this dynamical system theta is a vector field f from R2 to itself given by f of xy is equal to minus yx for all xy in R2. Okay, so we found the infinitesimal generator of this dynamical system given in example 2 here. Okay, good. Okay, so let me try to phrase it using different words. In other words, for this example, in other words, the dynamical system theta from R cross R2 to R2 given by theta t comma pq is equal to cosine t minus sine t cosine t acting on pq for all t pq in R is the flow of the linear system of differential equations. Okay, so we are trying to write this. Okay, it's a vector equation. Okay, it's a vector equation. So in this case, we are going to have d dt xy is equal to minus yx, since f is given by this, right? So we have this set of differential equations. Dx over dt is equal to minus y is one of the differential equations. The other one is dy over dt is equal to x. It's a couple differential equations, couple ODEs. Okay, good. Now we get to the concepts of fixed points and equilibrium solutions. Okay, fixed points and equilibrium solutions. Okay, good. Let theta from R cross U to U be a C1 dynamical system in U with infinitesimal generator f from U to R to the n. Okay, a fixed point of the flow theta in U is a point P star in U such that theta t comma P star is equal to P star for all t in R. So this is the definition of fixed point of a flow. Okay, so or equivalently, in terms of this UP T defined as theta T comma P, right? Using this definition, we can also write the definition of fixed point in the following way: UP star T, which is the same as theta T comma P star, is going to be equal to P star for all T in R. That's equation number 32. Recall, Q sub P of T is equal to theta T comma P. Okay. Now taking the derivative, with respect to T on both sides of 32, we obtain UP star prime T. So we are deriving this expression with respect to T. On the left side, I have the derivative of UP star T, and on the right side I have 0, because that's just a point independent of time. Okay, and that happens for all T in R. But we have seen earlier in the last segment, we have seen earlier that the following holds: UP prime T is equal to F of UP of T. Right. This is what we have seen earlier. So therefore, in the case of fixed point, one has UP star prime of T. Okay, so is equal to F of UP star of T, right? Okay, so if this is the case, then it follows from this and this, that F, so UP star T is equal to P star, and the left hand side here is just 0 from here. Okay, so this is equation number 33. Okay, so we thus see that thus a fixed point of the dynamical system with infinitesimal generator f from u to r to the n is a solution to the equation f of p is equal to 0. This is 34. So if you have a fixed point of a dynamical system, then that fixed point must satisfy this equation. Okay. Now, a couple of terminologies. Solutions to equation 34 are also known as equilibrium points. Equilibrium points or singular points. Equilibrium points or singular points. A point P in U which is not a fixed point of the system generated, so the system generated by F is called a regular point of F. Okay, now a solution to the system dx over dt is equal to f of x okay, defined by by 32. Let me write 32 for you here. Defined by 32, where 32 was up star t is equal to p star. Okay, this is 32. So if we have a solution of this system dx over dt is equal to f of x defined by this expression where p star is in u and that satisfies 33, which is, well, f of p star is equal to 0. Okay. If this is the case, then such a solution is called an equilibrium solution. 33 is called an equilibrium solution. Okay, an equilibrium solution. Now an example. I'll give an example now of fixed points. Last example of today's lecture. Consider the two-dimensional system. Consider the two-dimensional system given as follows: dx over dt is equal to lambda x plus y, and the other equation is given by dy over dt is equal to lambda y. So we number this equation by 35, where lambda is not equal to 0. In this case, the field f from R2 to itself reads f of xy is equal to lambda x plus y lambda y for all xy in R2. Okay, the equilibrium points are therefore solutions to the system lambda x plus y is equal to 0 and lambda y is equal to 0, which we number by equation 36. Okay, now since lambda is non-zero, the only solution to the system in 36 is the region, right? Because if lambda is non-zero, then if we want to solve it, the only way we can solve it is by putting y equal to 0 and x equal to 0, which is the origin itself. The origin 0, 0 in R2. Okay, thus 0, 0 is the only equilibrium point of the system given by equation number 35. Okay, so this ends the third lecture here. Thank you for attending the last segment of the third lecture.